Cool. I think we should be on. Let me just check. Amazing. Uh, cool. Yeah, it seems to be on.
Perfect.
Lovely. Alrighty. Are you good to start?
Yes.
Perfect. Okay. Hello, everyone. And let me just admit some people. Hello. Hello. Hey, Katrina. Hello, everyone. Thank you so much for joining us for this week's seminar. Today, I'm super happy to have here with us Schrodi. He's correct me if I'm wrong, but still a fourth-year PhD student at the University of Freiburg. Is that correct? Yeah, cool.
Yeah.
Still a four-year PhD student at the University of Freiburg. And he's going to be talking about today about his latest work on selective concept bottleneck models without predefined concepts, which, if I'm not wrong, was accepted at TIMLR last year, correct?
It's last year. Yeah.
Lovely. Okay, so yeah, please take it away. Thank you so much.
Yeah. Thanks, Matteo, for the nice words. And I'm happy to present here at the seminar, this paper. Yeah, this was obviously joint work with Julian, Max, and Thomas. And as Matteo said, it was published last year at Team R. And I'm super stoked to talk about this paper. So maybe let's get in, maybe for a more general audience, maybe first, like, why are we actually interested in concept bottleneck models, right? Because here we have these modern models, and they are now very accurate and they're super performant, and like we use them now essentially in our daily life. However, they're quite opaque. So they often give us the what, so kind of they give us answers, but not the why. And their learned representations are generally non-interpretable. And this kind of is not ideal for many applications where you care about interpretability. But then, like, at the same time, you also have these, if you think about your school time, maybe you had these books, right, where you saw these animals or like other things with a lot of errors where there was like, oh, this is a cat. The cat has 2 ears typically. Typically, it has a nose. Typically, it has some whiskers and eyes and has some fur. And like you have some concepts like you associate with an animal or like some other object or and like you could use this, right? And this is kind of the idea from concept bottleneck models, essentially. So instead of directly predicting the class, what we do is first predict the concept. From the concepts, we map them linearly to a cat. So here we do this via supervision, because like here we capture like data about like these concepts. For each image, we have like a full list, like is this concept present, yes or no, for example. Then learn this, and after that, we learn a linear classifier. And the nice thing about this is now the mapping from the concepts to the class is somewhat interpretable and intervenable. So this is quite nice. However, there's like two problems with this approach, three problems actually, which I will kind of now talk about. So one is like kind of, you need a lot of concept annotations, and often they need to be hand annotated by some humans. And consider that like we train here from scratch. That means, as we know, like what we learned about the last years in deep learning is kind of that we need a lot of data. So that means now all of a sudden we have to annotate not only the number of data points times labels, but which is typically one. Now you also all of a sudden have this other axis dimension where you have to annotate concepts. And this is quite expensive. And also this cost, I mean, this is like more wake here, might reoccur for every new data set. Another problem is kind of at the beginning, actually, you already have to fix the concept vocabulary that you want to use. So you want to somehow come up with a sufficient set of concepts, which later then can let you get a good performing model. However, this is quite hard to hit because likely you will either have too many concepts, so this just increases the costs, or you have too few, so you have insufficient concepts, so then you suffer for performance. And the bad thing here is like this wrong choice is already locked in basically from scratch. So you have to do like a long training and then and all of a sudden realize, oh, my model is underperformant. Maybe I just have to get more data. And this is quite, also from an organizational standpoint, a quite challenging situation, I guess. And the last point here is, at least when I wrote the paper, I'm not sure if this is true anymore, is that often interpretability comes with a performance cost. And this was quite substantial at that time, as I remember. And team had to change by now. And I think here the argument is very important, is kind of, actually what we also have to think about is that interpretability is a second, because performance is first. Because if a model is not performant, why should ever a user use it? I mean, there's some degree where people care about like that you have a really good model, and they might sacrifice interpretability just to get a better model, because maybe it makes their processes faster and solve solutions and stuff. And so this is something which is quite important also to consider. To remedy this, like, there was this line of work in 2023, which was on post-hoc CBMs. And here the idea is essentially we now cut this pre-training stage, which is the more expensive part, to get like this encoder, and convert the pre-trained model into a CBM. So here we start off with a large language model, which kind of gives us a set of concepts, or like a smaller concept library. Here the important bit that this is similar to the concept library that we would use for pre-training, like for the supervised CBMs. However, here the library likely can be smaller. So this reduces costs. Now we have like a set of concepts, and somehow we want to now get a concept representation for this. And there's like multiple approaches to get this, and this depends also largely if you use large language model or concept library. But there's like two popular ones are like concept activation vectors, where you kind of learn between a positive, negative set of samples, like a direction. The other one is like use just the clipped text encoder. It just depends on your application. There are some specifics which I now won't cover here. It's a part of this talk. But it's not important. I think it's just important that you just get some vector representation at some point. Now looking how you can now make like a prediction here. So again, you get this image of a cat. Then you have this this black box model, and then somehow you get a feature representation out of this. And what people have learned is kind of this feature representation is quite rich in semantics. So now what we can simply do is just do like something like a cosine similarity. You get a score between -1 and 1, which kind of tells you, oh, is this concept present in the image, yes or no, like continuous. And then you can use these later then to do the predictions on. So this is quite nice. And it resolves some of these limitations that I just mentioned earlier. So the concepts must be hand annotated necessarily, at least for the large language model at all. You don't need to annotate them. For the concept library, I would argue this is just like less, so you need substantially less. So also, I guess, fair enough to agree that this postdoc might resolve this. The concept vocabulary is also somewhat fixed, because like the large cost in training is like the pre-training, and this is done. So if you iterate over this concept vocabulary at this point, it might be way faster. And actually many people, obviously, if they, like folks, they test their methods, how fast they can train these CBMs, these postdoc CBMs, and this was, I think, roughly in 1 hour to 2 hours, which is essentially nothing these days. So, so this makes it also more flexible, and you get like this performance boost, which you get from this pre-trained backbone. However, there's one implicit assumption in all of this, and this is like somehow we assume that this model, that the large language model that we use, or this concept library, somehow knows what this our black box model has learned, that we previously trained on some other task. And I mean, I would argue this is a quite strong assumption, and I think this also might explain some of the artifacts that we will later see. And thus, I would argue that we should somehow get rid of the step, because somehow assuming that some other model learned something which we don't know that much about, so it's like a black box training, doesn't make too much sense. So maybe we should directly just use the representation somehow of this model and somehow get like vectors out of this. Maybe can we maybe shortcut this this part? The answer is yes. So let's start what we can do here. So first, kind of we get a full data set of a lot of images, or like any other modality. Then we get this pre-trained model, download Dino, whatever, your ResNet, favorite ResNet, whatever model, and you get a lot of features. Now, somehow we want to get these concept representations out of it. And the nice thing is there's actually an orthogonal direction in the literature, which is called like concept discovery or unsupervised concept discovery. And here is exactly, you have these activations, you stored them all, you have this big matrix, and you now want to decompose this into two components. Like U, which is like your sparse coefficient matrix, essentially for each input, it says kind of how much of the concept in the concept bank, so just like here are living the concept vectors, do I want to reconstruct these activations. And the nice thing is actually you can summarize them all as Phil did in this dictionary learning setup here, where you just try to approximate these real activations. However, if you do this now in unconstrained manner, kind of you don't get really interpretable like concept out of it. So typically what you do is you apply some constraints. So one is like, for example, k-means, where you say, yeah, each input can only be associated with one concept, essentially. The other one is like PCA, where you impose orthonormality on C. The other one is non-negative matrix factorization, where you say everything must be non-negative in U and C. And since then, we can only add, and there's no cancellations. This somehow makes the model now learn like this decomposition learns like a part-space representation, which makes it interpretable. And the last one is like sparse autoencoders, which got popular lately, where you replace this U with some encoder, can be actually nonlinear, and then you get like interpretability by forcing a sparsity constraint on this encoder. Here we selected non-negative matrix factorization, and the point is there's no reason why you should pick exactly this method. And actually now, if I rewrite my paper now, I would probably use an FAE or something even newer, I guess. It was just a choice at the time when we started the project that we committed kind of to this non-negative matrix factorization. However, I think this doesn't play too much of a role. It's just like kind of a hyperparameter choice. Okay. But now the question is, do we actually get like really good concepts out of this? Because I mean, this is unsupervised manner. I mean, there's no reason to believe that these are any useful. So typically what we here can see is like kind of you get like this, and here you have this image of this rabbit. And then we kind of get like cosine similarities between the vectors and this, like these concept vectors and this feature vector from this. And then we can kind of visualize here, the cosine similarity, and then the most activating other image patches, which kind of represent now this concept. And as you can see here, like we find this image response, there's this concept, which is super important, is like the eyes or the face of this rabbit, then the fur, ears, and so on. So it's quite interpretable. There's a really like sensible concepts that you get out of this. But the question is, are they actually faithful, or are they just like just listed? And to test this, like what you can do is like, let's take these ears and just remove them, right? So here, this is hard to see, I guess, and maybe on a smaller screen, but here we just replace the ears like with this wooden, whatever this is, bad thing. And then as you can see, is all of a sudden this concept is gone. It kind of gives you the nudge that these concepts actually are interpretable. I mean, I won't go too much into detail because, I mean, this is mostly also the literature that concept discovery is focusing on, but like we did a lot of testing around this and they seem quite sensible most of the time. I mean, also come to this limitation later. Okay, what we now have, actually, we have to solve the issue that we talked about earlier, right? Because now what we have is like these concept vector representations here. And now we can just do the linear classifier, right? So again, we get an input sample, you get the pretrained model, get the features out, and then somehow get an alignment score. Like here in this case, we use the cosine similarity. And now we can do a linear classifier on top of that, right? And then that's it. Yeah, so, but the question is actually, is this linear classifier even interpretable? So again, we get here these vectors, we get vector, so here's just text, but we get here vectors you can think of, and then we do like here this linear model. However, here's the issue that like we might have like a large list of these concepts here. I mean, this could be hundreds or even thousands, so it's like a lot. And this makes also, I think, this linear classifier very non-interpretable. This is what people often don't think about, is like this dimensionality thing. Because as you add more and more concepts, at some point, like it gets very hard to understand. Because if everything contributes to some extent, it's really hard to see, oh, this is adding plus 0.1 to the logit of this class, and this other one is adding minus 0.2 and so on. This is very hard to understand. So maybe somehow can we make it sparser to make it easier? And the first thing what you can do is obviously go to the weights. So make them somehow sparse. And this is actually what also people did. And here we just apply an elastic net or a one penalty on the weights. So essentially what happens here is we have here for the rows, we have like the classes, and the columns are like the concepts. And before, like we have a lot of non-zero entries here. And with this penalty, essentially we force a lot of these values towards zero, which are like non-important. For example, to predict the cat, the roof doesn't play that much of a role and should like be kind of 0. So it should not influence the prediction for the cat. Yeah, so basically what we get out is a matrix with a lot of zeros, and then essentially each class now relies only on few concepts. And few means here like 20 to 40, still a lot. But I mean, still it's like less than like thousands or hundreds. So we reduced the problem already quite a bit. But now let's say we have learned this, right? And this cat now relies on the eyes and the nose and stuff, on all these concepts. But I mean, this works quite nice for this image, right? Here the cat, we see the eyes, so we have a large weight on this, and then this gives us a sensible logic. However, what happens now if the cat is not looking at us, right? I mean, this happens. Cats sometimes don't look at you. I mean, they are like, sometimes they also mind their own business, I guess. And then we don't see the nose, the eyes, and the whiskers. And if you look now here in this linear model, then we have a kind of, we have this W of large weights, and concept scores also often are non-zero, as it turns out. And then what happens is kind of that all of a sudden these non-visible concepts still have a relatively sometimes large influence on the prediction. And this is very non-interpretable and non-sensible, I guess, that these concepts which are non-visible have such an impact. So maybe we look just now also at the concept scores, right? Maybe we can also specify them here, and this is kind of the next idea. What we want to do is, like here at the top, we see like all of these, for each concept, you see these scores, and what we want is like to cancel a lot of them out, because likely they are not present in the image anyway, so they should not influence the prediction at all. So the simplest thing actually what you can do is just use the top car function. So here you just use the top car concept or alignment scores here. And we add also here this always positive trainable parameter. This is like if sometimes concepts like these scores might have different distributions and they might be shifted, and this O couldn't correct for this. So this is more like a correction term. And we can control the sparsity directly via car, right? So if you set car to 1, then only one concept influences for any input always. But input dependent, there's one. So basically what happens if k equals 1 is, given the input, we just pick the concept with the highest score and then make the prediction from that. And then if you do larger numbers, then it's like more concepts, obviously. There's also other options. I will quickly skim over them because, I mean, top car works best. But you could do something like a ReLU kind of thing, where you you apply like this elastic net regularization on the output of this ReLU, basically pull it towards 0 and hope that many of these values land below 0, so they cancel out. This is also one option. The other one is jump ReLU, which essentially allows you now to optimize over this L0 penalty, which you actually are interested in, because L0 typically is non-differentiable, but it's jump ReLU with some tricks makes it differentiable for you. Yeah, this is this is more like a choice. I think there's also, you can do way better options here. This was more like a most simple approaches that we found. Okay, now we have the concept selector, which basically cancels out a lot of the concepts. And we have now this final classifier, which we can now train, right? So now we have like this classification loss here with the concept selection part. Then we have per class regularization, which we also will add. And finally, we have this input independent regularization term, which we now added to. And this is all now. We have our full also sparse classifier here. And coming back to the method overview, we now finish this off is like we get this input dependent concept selection and then the sparse linear classifier. And this basically is the method that we introduced here, or the framework. And now maybe let's look into how this method actually works in practice. So I talked a lot about sparsity, and we defined this term now here to show like there is a sparsity issue. So here the idea is, first we check, is this concept actually active? Because if it's 0, then it cancels out, right? And then we have the second part is, does this W, is this non-zero such that the concept has an influence on the prediction of any class? Because like, remember, classification is a discriminative task, so only looking at the predicted one is actually a bit insufficient, I think. You should actually, theoretically, I guess, look at every class to understand actually why was this one picked, because maybe, yeah, there's weird things going on, and it explains you better how the prediction works. So here we computed like now this ratio where we now have this mean number of active concept, which is defined as with this equation, and divide this by the total number of concepts. Reason being that they have like all these methods, also ours have slightly different number of concepts, and to make them comparable, we make this now relative. As you can see, actually here, like if you look into postdoc CBM or label-free CBM, essentially you almost use for every prediction all the concepts to some extent influence the classification in some way or the other, which is not ideal. And like VLG CBM is in this term with this regard a bit better, but still like a lot of the concepts are influencing. Now coming to UCBM, we see without concept selection, okay, as expected, we get like 100%. So we always use all the concepts, which is like exactly the worst case scenario here. And there was also this other paper, which we later found had a similar idea, which used the binary indicator, and but it also didn't like get the sparsity levels really down. So now coming to the concept selectors that we did is like we see like large drops in this metric here, where we see like, for example, in ImageNet, only 1.4% of the concepts are used. I mean, the thing is, maybe one important bit here is to take this number a bit into context is here in this case, these methods roughly use 4,500 concepts, ours use 3,000. So actually the total number of concepts is even lower, but also in relative terms is lower. So what we see here, like these sparsity panel, these concept selection actually have quite a big effect on these predictions. But now you could assume, okay, maybe now we lost all the performance, right? I mean, if we for each import cancel almost all the concepts out, you should get good performance, right? Turns out this is not the case. And so here again we see like in previous work and the original black box model as a reference. If you now look into without concept selection, which is like or kind of reference here, we see like we already got good numbers. This also shows actually that this first part, this unsupervised concept discovery, likely detected better concepts, which are more generalizable and probably also better than these previous works that had this large language model or clip-based approach to get the concepts. So we get a boost from there. And the good thing is the sparsity doesn't hurt that much. So actually what we see here, we only get like sometimes very small drops in performance, like 1 to 2% with these high levels of sparsity, and still like get better numbers than those. But for KUB, where VLCBM is better. So this is quite nice. So this kind of shows you like, yeah, actually we can get a lot of sparsity, but still get very good performing models. Good. I mean, this kind of concludes kind of this more numbers-based part, and I want to come more to this interpretable part, because that's also very important. And here we look just like, okay, we given an image, what are the concepts that matter for that prediction? And here UCBM predicted correctly limousine, and as you can see, like it relied on a lot of concepts which are quite sensible. Here we labeled them by hand, looking at a lot of images, and also used in large language models to support us a bit because there were many concepts. Yeah, but here we saw like, yeah, focus on large back windows, which kind of is true maybe for this window or so on. But then round the metal edge, car body, car window, and black white contrast all are present. So this prediction makes quite some sense. Given these concepts, you could see, okay, why the model predicted that class. If you now look like into label-free CBM, it also predicted limousine correctly. That's nice. However, it focused on a lot of concepts which are actually not present here. And I think many of them are correlated with the class itself, the limousine. But these concepts are not visible, unfortunately, for that image. For example, there's no chauffeur, at least. I zoomed in, maybe there is one. I might miss them, but I don't see that. And also, there's no wedding. I think this is more like, looks like more like a typical, I mean, I guess, auto conference venue where they park this limousine. So, I mean, these concepts, kind of this explanation, I think is not that helpful here. And lastly, and we also compare to real CBM, but essentially you get the same thing here. So it says special occasion. I mean, it could be a special occasion. I mean, this is fair, I guess, but it doesn't really help you to understand what's happening. And here's also the point, like, yeah, in fact, here's like the key benefit of UCBM because it's very grounded in this first gets like the features that we see the concept and then predict from them, which maybe these other methods for reasons like they find these maybe spurious correlations because maybe the concept is not really learned and so on, find these weird like concepts then. However, I think this is not that clear here because like often like what people do is they show like these exactly these examples where every model predicts the correct thing. But I think actually what people should look into is what happens if the models predict the wrong thing, right? Because this somewhat disentangles kind of, does the model give you the right explanation for the right reasons, or does the model give you just an explanation to make you believe it had the right reasons? And for misclassifications, there we kind of disentangle both of them. So here, like this was labeled as a PR in the ImageNet data set, and UCBM predicted a boathouse, which makes, I guess, to some extent sense. I don't know. And also the concepts that it used are quite sensible. So they're all present in the image here. You can find them. To some extent at least. I mean, ship reeling, I guess not, but maybe also this labeling is wrong. I'm coming to this limitation in a bit. But I mean, essentially, yeah, it somewhat makes sense. You can understand what happens here. Coming now to like these other methods, is like you have label free CBM, it predicted this as military uniform. And all of the concepts actually are non-present at all. And this kind of shows you kind of that like this method might give you an explanation, but the explanation might not just confirm what the class is, not what actually it was based on, because it just comes up with these concepts which are non-present. And lastly, also VLGCPM, it predicts here gas mask. Yeah, and these concepts have nothing to do with this image at all. So I think it's hardly interpretable. And this is like, just to be fair here, this is a random example. So this is not cherry picked, it's just like I find where all the methods do one error and then just pick them. I mean, in the paper, we have a couple of them. I mean, I think it's very worth, if you do like this research, to look into these cases because they kind of give you, I think, a better understanding if actually your model uses the right concepts and if it's sensible. Because if you do always only correct, I think it can be misleading because then it just predicted the correct class. And these, you could argue here, yeah, these concepts somehow you could see them in the image. However, like in the case where you have like these misclassifications and they're non-present, this is very obvious that there's something off. Okay. Yeah, and then last, what I would like to talk about briefly is like, yeah, interpretability, because it's also an important bit. And here we did a way too complicated, essentially, approach to this, where we had a misclassified, this image misclassified as a goose, and the correct label would be flamingo. Then we provided like a text prompt to a large vision language model. In this case, I think this was GPT-4 at that time, with like concept inference, a lot of information about the models and so on. And then we asked that, hey, please, can you change our weights in such a way that the class is correctly predicted as flamingo? And it actually could. So here you see like this concept, which I guess corresponds to pink feathers, which you, I guess, could see here and here, like is upweighted here. And these other like features, which are more like, I guess, goose-ish related feathers are down-weighted. So yeah, it's kind of explains, so kind of it shows you that this approach also intervenable. This is more like to the design of the linear classifier, not specific to our method. All of these methods have it, but I just wanted also to show this example here. Okay, now coming maybe to limitations, which I want you like, which I think are worthwhile to mentioning here. And one is like definitely that the concepts are represented as visual like concepts. So when we label, because we don't get labels, right? We just get like, we basically get these concept vectors and then find the highest activating images for them. Then get the highest ranking, look at them and try to figure out what do we see here. And if they're monosemantic, it's kind of easy. Then it's like, that's quite nice. And actually many of them are monosemantic, as it turns out. I think we did like a small study on that, and that was like roughly 80 to 90% ish. So this was quite nice. However, there's also these polysemantic concepts, which are harder to interpret. Like you have this light tower, and but then you also have these two dogs and these clocks, I think they're called. Um, and this is very hard to interpret what this actually means. It might be like there's maybe some vertical thing in the image. I'm not sure. This is very hard, but so this somehow hurts a bit of the interpretability because some of the concepts are a bit like polysemantic. And the other thing is sometimes we also don't know what the concept may include because now if you look into this, like the first like 6 images, you could maybe or even 7 images. Okay, I think this is a cyclist too. So in the first 6, you could say, oh, maybe this motorcycle racing, right? But then you look into the top 7, 8, 9 images, and all of a sudden you see like a cyclist, 2 cyclists, and like a baseball player. So maybe this is corresponding to safety equipment. However, the general point being here, sometimes these concepts are not that easy to interpret because you have to look into a lot of these images and somehow draw your own conclusions. Like current vision language models, at least at the time when we tested, were not that capable to aggregate like the common concepts in like in a set of images. But yeah, that's something which is a big problem here and can hurt interpretability. The other limitation I think worth mentioning is like that somehow we shifted a bit of the problem here. And this is a broader point, I guess you could argue, is that somehow we shifted kind of the non-interpretability part from the class label to the concept, because still there's this very non-interpretable part here where we just predict like these concepts. And you could argue, okay, now we have partly solved interpretability, but I think it's also worthwhile maybe, which I would find very cool if you maybe get like a model where we have like intermediate concept bottlenecks in some sense, like a low level concept bottleneck where we find maybe the color of the eye or the pupil or like this claw here, and then have like not smaller non-interpretable parts in between which then build these higher level concepts later and so on. I'm not sure if anyone did this. I would be very excited if someone did or if someone will do it. But I think this might be also a very interesting direction. And also as a kind of limitation because also we only use the features at the last layer. And definitely there are also good features at the previous layers, but also for our methods that we could leverage to some extent in some way. However, we did not do this. Okay, to summarize this, like what we did in this work is like we just use the concepts that the model has learned. So we don't say, hey, this pretrained model, please give us the concepts that you that we want you to have. We just essentially ask the model to some extent if you want to anthropomorphize this, what actually are the concepts that you have learned. And the important bit is that we don't need to predefine the concepts. We just use the concept that the model gives us. Yeah. And the other thing is this input dependent selection mechanism here, where we try to keep only the concept that are visible in the input. I mean, obviously that might be better methods that you can consider. I think there's a lot of work that has been done on this actually. And I think, yeah, but I think this is very important that the classification only relies on things which are visible in the image. Because if it relies on, if let's say user sees all of a sudden it relies on a feature, like a visual feature or anything which is not visible in the image, I think they might question to use this tool the next time and look into this plot. Because I mean, it's non-interpretable in this case. Very obviously. And the last thing is that yeah, UCBMs are like quite sparse. As you can also see here in this Pareto font visualization here, where you see the test accuracy and these active concepts, but they're still very accurate. So you still like are competitive or better than previous postdoc CBMs. Yeah, and that will be it from my side. And thanks for your attention.
Amazing. Thank you so much, Simon. That was really great. Um, do you know if I don't know if anyone has any questions? If you do, please obviously feel free to just unmute yourself, or you can raise your hand. Any questions? Check this here. Um, otherwise, I have a couple. I'll start, and then if someone has any questions, do obviously interrupt. Yeah, of course. So I know you mentioned that you would do differently now, the non-negative matrix factorization part of it.
Mm.
Um, but do you recall at that point what was that the decision? Like in terms of, because it seems like there's no non-negative matrix factorization compared to other approaches like say topic modeling. Um, has a strong assumption that these directions cannot they cannot suppress each other. Right,
Mm.
they always have an additive effect on each other. So
Mm.
there's not a concept that can suppress the presence or the lack of another concept. And I wonder if you think that has any impact on what you would observe you would do today with something that does not assume that, like say essays, where the scores have to be positive, but the actual vectors could live anywhere in the real space.
Yeah, definitely. I mean, this is a strong assumption. I think this is actually not true, especially for some feature spaces where you also have negative numbers, I guess.
Hmm.
Because I mean, look at the clip embedding space, for example. There you use hypersphere, and that's a bit weird because then you only get like this one part at the top where everything is positive. So this makes a bit of strong assumptions. Likely you won't find that many concepts. In our case, it didn't matter that much. This was more like a technical thing because we use the ResNet oftentimes as a backbone. And this uses a relu, and relu, then everything is positive. So
Hmm.
there we don't run into this issue that much. But for example, for transformers, this is a bigger issue. And there definitely, I would recommend using something like an SCE or something like that.
Okay.
Because it does make sense. This was more like a bad choice, I guess. Now looking back, yeah.
Yeah, and also because I was about to mention you extracted like 3,000 concepts. Is that correct? Something like that?
Yeah, yeah.
Because then non-negative matrix factorization is quite a hefty, computationally hefty method, right? It takes, I don't know, I haven't used it in ages, but I remember it used to be quite a lot when you have quite a lot of data, particularly.
Mm.
Was that a limitation ever, like in terms of how much you could do, or was it always related to extract this?
You mean the 3000s? Why we didn't pick more or less?
Or in terms of the computational sort of cost of running a non-negative matrix factorization?
Yeah, I
So,
mean, this was a big thing. So I at some point, I mean, I think there was a public implementation, which was the sklearn implementation that uses CPU, and then I used that and ported it to a GPU base, and that made things way faster. But then you still had to do kind of clever tricks to somehow scale it.
Mhm.
So this was actually also something which we ran into later, which turned out to be a bad choice by we using this method because yeah, then I think we went to a, as I remember, we did to a batched version of it, I think, at some point. That's
Mhm.
alleviates a bit, but still these matrices, these U and C matrices are super large.
Yeah,
And this is like non-ideal because essentially it's like the number of data points, right? And then
and the
number
number
of,
of dimensions of the latent space, right, which could also be quite large, I guess. Also,
yeah, I mean,
yeah,
it depends how image is 1 million times 1,000, I guess.
yeah.
But it's, I mean, either way, it's like not a good. Wait, it's yeah. I mean, not a good idea. To do this. You have to do a bit of like implementation to make this work. Again, other methods are way better in terms of computational getting them faster. Or let's say they're less computationally expensive
Mhm.
like you don't in memory footprint.
Yeah.
Yeah.
Yeah. Cool.
I
Um,
also would have a
yeah, cool.
question, if I may jump in. Simon, thank you for the nice talk. And I was wondering, you mentioned that UCBMs, they can be used with different backbones. So I was wondering if in terms of interpretability, you noticed some differences with respect to the backbone used.
This is a good question actually, and I think this makes a big difference. But I'm not sure if I ran different ones to be honest. Let me think. I mean, I think we didn't do that much looking into this, but I think this is worth also one of the hyperparameter choices to optimize over. For example, I think there's some embedding models or encoders which are super strong. I mean, be it Dino, it's very strong. Clip, I mean, given my other research, I have some doubts about this space a bit, but yeah, also Chepa is also. So I think looking at in different backbones is a very good direction to look into. because I think we can get way better concepts here. And I think Dino is actually almost made for this. But we stick with like kind of a previous literature did to just be comparable in terms of numbers. Yeah, but
Mhm.
yeah.
Cool. Are there any other questions? Anyone else have a question? I guess actually, I'm actually kind of curious about so if you have, how do you select the number of concepts you discover? And then I guess after that, how do you actually went around interpreting most of them? Because you say you didn't use an automated pipeline for that. So if you have 3,000 plus concepts, that seems, yeah, a lot. So I'm just very curious how did that work?
I mean, yeah, we did partial sampling to some extent. I mean, mostly, I mean, we asked one thing was like we ran like vision language models and that seemed to
Hmm.
scale, but then often we found them not really good concept descriptions. I think it's a more general problem. And then we did a subset of them, which was mostly when we plotted and saw like these concepts. Like, I mean, essentially when we did these plots, so we had these plots before without these names here. And
Hmm.
then we looked afterwards at the names. So kind of to be
I
more
see.
unbiased on this. So we didn't want to have bias. Yeah, and then picked like a subset of them. We actually didn't label all of them. This was more like a time constraint. And I think this is a big issue that we had to label them. And I mean that no automatic method is possible at this time. Also, I have to be honest that Julian, my co-author, did a lot of them actually. I think he did 1,000 or so, 1,000 to 2,000 something. You know? I don't he did a lot actually. He was for
Well,
full weekend. I don't know. He got into the room and then labeled them. And I mean, it was quite impressive because I asked him, "Hey, can we label them?" And he was like, "Yeah." Then I thought that he would do some automatic pipeline and so on, but then he labeled.
That's wild. All right, because yeah. By the way, this is not this is a recurring problem in a lot of things. Like it's quite a common thing, for example, in bias detection and mitigation, when you try to identify error slices and so on. And yeah, you can do a little bit fancier bits, like using automatic captioning and then trying to find keywords in all the captions that are shared across the images and so on. But yeah, they're always a bit iffy. So I was curious if that's. I do think right now the best option still is unfortunately manual, just manual work into this. Um,
Yeah, yeah.
cool. Um, all right. Does anyone else have any questions before we wrap up? If that's not the case, then well, thank you so much, Simon. I really, really appreciate it. It was great. Really, really liked it. So really good work.
Yeah.
And
Thanks.
thank you so much, everyone, for joining this week. I think we have next week. Yes, we do. Yeah, so next week actually Oscar is going to be presenting. He's one of his active papers. So do come by same time as always. And yeah, appreciate it. Thank you, everyone.
Thank you. Bye bye.
Okay, bye.